Well, greetings, mathletes, and welcome back. So we're going to spend a little more time talking about the graphs of tangent and cotangent today. Last time we took a look at what their basic shape was, but we really didn't explore it very deeply. And then some of the things that we're going to take from graphing tangent and cotangent, we're going to turn around and come back and look at how those things apply to sine, cosine, secant, and cosecant. So let's go ahead and get started here. Let's see, we got that. Everything's on. Okay, good. So let's take a look at, so we have f of theta is a tangent theta, or excuse me, let's try that again. You can tell I'm getting tired already. So a times tangent b theta plus c. And we want to see what happens with this graph and with, of course, cotangent, same thing. A cotangent b theta plus c. Okay, so first of all, I want to remind you guys of the basic structure of the graph when it has not been shifted, right? When it hasn't been altered in any way. So unaltered, tangent has asymptotes at pi over 2 and at negative pi over 2. Ooh, my handwriting's bad on this today. And then it kind of goes up this way and back down this way. Now, there's another point in here, and we kind of briefly talked about it, but at pi over 4 and at negative pi over 4, the unaltered tangent, right? So a here, this guy is 1. When a is 1, this piece right here, the one at negative pi over 4 and pi over 4, is going to be at 1 and negative 1. Now, in general, what ends up happening is those points end up being at a and negative a. So I'm going to rewrite that. So this is at a, and this one down here is negative a. Right? So we actually have 5 points that we can use to graph tangent with. Right? We have the two asymptotes, those are your outside pieces. Then you have your center, the halfway mark between the two asymptotes. And then you have the quarter marks, right? So really, when we graph this, we want to break it up into 4 pieces and see what happens at each of the boundaries, right? So the key points we're going to be interested in with tangent are going to be these, the ones where we have things marked here. So we're going to be interested in negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. And what these are, I'm going to call these key arguments. And an argument, when we're talking about trig functions, an argument is what you shove into a trig function, right? So in terms of this tangent, the entire b theta plus c is the argument. Okay, so over here with cotangent, let's go ahead and draw the graph again, just like we did this last time, because we're going to have key points here too that we're going to care about. So let's see here. Let's go ahead here and here. And then cotangent ended up, the two asymptotes for cotangent were the y-axis, or I guess it'd be theta in this case, and at pi, right? And so we still had a middle point here, and we actually have these 2 points here. And if you remember the graph, cotangent, let's just take that off of there. That was pretty bad. Let me change the angle on this so I can draw it. right? Cotangent does this. It doesn't cross the y-axis, so there's no y-intercept for cotangent. Um, we have our 0 point here, and then these points for A that we have over here in tangent are actually over here. So if this is 1 and this is -1, right? And let's just make sure we're clear. This is pi over 2, pi over 4, and 3 pi over 2. At pi over 4, I'm at 1, and at 3 pi over 2, I'm at -1. And furthermore, if you generalize this to A, it's not 1 and -1, it's A and -A that those things are at. So if this was 3 cotangent, this thing would move up to 3. And so it just stretches it out a little bit. Same way it does with sine and cosine, right? It stretches the wave this way. Well, this is stretching the tangent or the cotangent the same direction. Okay, so let's go ahead and look at a more specific example of tangent and see how this is done. Okay, so let's go ahead and clear that off. And let's say I am given f of theta is equal to, excuse me, 3 tangent theta. Okay, so the argument is just theta. It doesn't have the whole business in it, you know, with the b and the c or anything like that. So I don't really have to worry about too much on that. If I'm going to graph this thing, I know, let's see, it's unshifted, so that means I have asymptotes at pi over 2 and negative pi over 2. This thing, so that's positive, so that's good. I'm going to mark in my 3 and -3, and then I'm going to mark my halfway points here. Okay, so when I graph this thing, what I want to do, I know this is, the pi over 2 is the asymptote, but at pi over 4 and negative pi over 4, I know I have a point here and a point here, and that's just from this guy, right? And then we still have our 0 because it hasn't been shifted. And what we do is just connect the dots, right? And so we have that extra anchor point that tells us how stretched out this is, right? That's, and you notice again, it's broken into quarters. We have 1, 2, 3, 4 different regions here. And that's the same thing we did with sine and cosine, secant and cosecant. We broke it into 4 pieces and found what happens at the quarters. Okay, so let's look at one more here. As a matter of fact, let's go ahead and clear this entire thing off. We're going to actually, this time, we're going to look at what happens when you have a period change or a phase shift and things like that. So, let's see here. Let's look at, oh yeah, I have to turn the pen back on. So let's say f of x, it doesn't actually matter what I use as a variable, I'm going to use x in this case, is 2 tangent of, excuse me, let's do 2x minus pi. Okay, so we got some stuff going on here. Now, if you want to figure out what your period and your phase shift are. Now, before with sine and cosine, secant and cosecant, it was always 2 pi over b. And that's because the period of those 4 functions is 2 pi. But the period here is pi. So the period is going to be pi over b. And b in this case is 2. So the period's now pi over 2. So it cut the period in half. It did have a period of pi. Now it's pi over 2. Excuse me. Now we need to have the phase shift. And you find the phase shift by taking the argument and you set it equal to 0 and solve. And that will actually give you your phase shift. So if I do this, I'll add pi over, divide by 2. My phase shift is pi over 2, which means that it's scooted over by pi over 2. In fact, since this is positive, it's moving, it would be moving to the right pi over 2. Now, you have those things, and those are good things to know, but there's actually easier ways to graph these things. Okay, remember when I told you about using your key arguments? And for tangent, your key arguments, so if you remember them, would be negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. Okay, I'm going to run out of room if I'm doing this. How do I want to? Well, I guess we can still probably squeeze it in. Okay, so what you do, this is what you do with the arguments. I'm going to change the color so we can tell where they are. You take the argument, 2x minus pi, and basically what we're doing, if it was unshifted, these would be our x values, right? Those are the values where we put things on the x-axis. What we're going to be doing is shifting those around so that we can see what the new values of x will be after it's been shifted. And so one at a time, we take this 2x minus pi and set it equal to each one of these key arguments. Well, I put 0 down first because I was thinking cotangent, but so it'd be negative pi over 2, and then we have it set to negative pi over 4, and then 2x minus pi is 0. 2x minus pi is positive pi over 4, and then 2x minus pi is pi over 2. Right? So we want to solve each one of these for x. So this one, if I go ahead and add that over, that should give me x is equal to pi over 4. Okay. This one, if I add that over, that ends up being, let's see here. If I subtract the thing over, that gives me 3 pi over 4. That gives me 3 pi over 8. Yeah. And then the 0 we actually already did, right? The 0 was pi over 2. And then over here, now we have the positive values. So if I go ahead and add pi to that, that's 5 pi over 4. So this ends up being 5 pi over 8. And this last one ends up being, oh, I think I said fifth point, and then I wrote a 5. Over here, if I do that, that's 3 pi over 2, so that's 3 pi over 4. And I'm going to leave you to work out the algebra on that. But we have our key points. These guys, and I'm going to write them down here and then erase this stuff. Once we solve these equations, basically what happens is whatever point was at negative pi over 2 is now at pi over 4. Then 3 pi over 8, and then pi over 2, and then 5 pi over 8, and the last one is 3 pi over 4. Okay, so that's where everybody translated to. So let me get rid of some of this stuff so we can actually graph this thing now. Let's do it this way. Okay, so let's put these guys in here. So it's shifted to the right. And you notice this method here, you actually don't even need to know what the period is. You just need to see where these points go to. So the lowest point is pi over 4. So I'll say that's pi over 4. The highest point is 3 pi over 4. Pi over 2 is the halfway point between them. And then the other halfway points would be 3 pi over 8. And, ooh, that's not a very good one, but, and then 5 pi over 8. Right, so those are your new points. There we go. Now, what that means is that our asymptotes are on the outside points, right? The 0 is right here, right? Then you move to your right and move, or yeah, I'll move to the right first. And at 5 pi over 8, since that's the 3/4 mark, the value there is going to be whatever a is. Now that's a 2 in this case. So that means that it's going to be at 2 here and at -2 down here, right? And then we can just draw the rest of this in. And you notice it was just using a little bit of algebra to figure out where those points move to. So once you understand the basic graph of this, all you have to do, because you will be asked questions what the period and what the phase shift is and stuff like that, and you can compute those just like I showed you here. But when it comes to actually graphing it, you can just manipulate these key arguments and go from there, right? So if you can break up one period into quarters, those are going to be your key arguments every single time for every single trig function, not just tangent and cotangent. It's always about the key arguments. Okay, so let's take a look at one more example. We'll try it with cotangent this time. Okay. All right. So let's say we have, let's see, that's on, oops. F of x is equal to -3 cotangent 3x minus pi over 2. Okay, so, just as before, the unshifted period is pi, right? So if I want to figure out what the period is, the period is always, let's see, the period is going to be whatever the unshifted period is divided by b, and in this case, 3 is b, so the period is now pi over 3. Right? Okay, now, if you want the phase shift, what we do is we set this argument equal to 0. So let's see what we have here. Let's see, I would add that to the other side and then divide by 3, and I would end up with x is equal to pi over 6. So our phase shift is pi over 6 in this case. So it's shifted pi over 6 in the positive direction, right? Because this is a positive number. If it was negative, it'd be moving in the negative direction. Now, honestly, again, just like before, I don't find it very convenient a lot of the time to use the period and the phase shift to graph it. Those are useful things to know, but when it comes to figuring out what happens, you want to be thinking about the unshifted graph and what the key points are. Now, cotangent runs between 0 and pi as far as what's graphed between asymptotes, which means that sorry, wrong function. Right, which means it does this business. And this would be at pi over 2, this would be at pi over 4, and this would be 3 pi over 2. Just, it's still taking that period of pi and breaking it into quarters. And again, a and negative a are these points. All right, so a and negative a end up at those points. So it's very similar. You just have to know what the unshifted graph looks like. Now, what that also means is that we can just use these key arguments. In fact, we can see the key arguments are going to be 0, pi over 4, pi over 2, 3 pi over 2, and pi. Right? Those are going to be our key arguments. So our idea is to figure out where those things are going to move to. So what we're going to do is take the argument of cotangent and set it equal to each one of these things. So if 3x, I want to do this taking up less space. Let's make a spot. We'll just do this. And then we'll just match them up here. Okay, so we'll start with, actually, I'm going to switch colors too, just so it stands out a little more. Turn the pen on also. 3x minus pi over 2 equals 0. 3x minus pi over 2 equals pi over 4. 3x minus pi over 2 is equal to pi over 2. 3x minus pi over 2 is equal to 3 pi over 2. Oh, 3 pi over 4, excuse me. And then 3x minus pi over 2 is equal to pi. Right? So those are our main things. And then what we're going to find, we've actually already computed the first one here, right? This one changes to a pi over 6. So I'm going to write that in here. And then the second one ends up being pi over 4. Right? The next one ends up being pi over 3. And so that goes here. And then the next one is 5 pi over 12. Oh, these are getting crazy, huh? And it's a good idea for you to go through and make sure that you can compute these things yourselves. I'm kind of going through this quickly because it's just some algebra, but sometimes it feels a little weird dealing with that pi in there. So if you need help with it, please ask me about it. And the last one here comes out to pi over 2 once I solve these things. So what that means for our graph is that these are now the key x values that I need to use. Those are the ones that are going to define one period. And I see it runs from pi over 6 to pi over 2. So I'm just going to put pi over 2 out here. And I'm going to put like pi over 6, I'm going to put pi over 6 over here. And then what I need to do is divide this into 4 pieces, right? Because this will end up being one period. So this is one asymptote. This is the other asymptote. You notice what I did, I used my high and my low point to start out with. And that means the halfway point is going to be, let's see here, that's at pi over 3. And then we have pi over 4 and 5 pi over 12. Right, those are my key points. And from here, I know that at pi over 4 and 5 pi over 12, because those are my 3/4 marks, that's going to be a and negative a. Now, I have an interesting dilemma here. At pi over 4, it's supposed to be a. A is a negative number, which means it's down here. And at 5 pi over 12, it's negative a. But again, a is a negative number. So that means negative a is the positive number, right? And then we still have our 0 here. And then this thing will then continue this way, right? So it should look something like that. And that is one period of this. Keep in mind, this thing actually, did I do that right? Yeah, I did that right. This actually repeats itself. So this thing will, right, there's more of this as we go. We're just looking at one period of it. Okay, so, using these key arguments, the key argument technique is actually quite nice as far as graphing these things. You can do the same thing with sine and cosine, and I think we did it a little bit in the past, but I think what we'll do is we'll take one example of either secant or cosecant now, and we'll graph that, because we'll either have to graph sine or cosine to be able to graph secant and cosecant. So let's take a look. Let's see what we got here. Okay, so let's go ahead and take a look at this here. Let's say that f of x is equal to -3 secant 2x plus pi. Okay, so a couple of things here. Amplitude, right? We should be able to pick that out right away. It's a, the absolute value of a. So it may be a negative it may be a negative number here, but we always take the amplitude as positive. The period is going to be, well, the period of secant is 2 pi, so it's going to be 2 pi over b. B is 2, so the period is pi. Okay, and then the phase shift, right? How far to the left or the right it's moved. Let's see here. What we do is we take the argument, 2x plus pi, and set it equal to 0 and solve, and that will actually give us our phase shift. And so our phase shift is negative pi over 2 in this case, right? And if it's negative pi over 2, that means it's moving to the left, right? It's moving in in a leftward direction, so to speak. I don't know, is leftward a word? Westward? It's west. It's moving west. Okay. Now, what we can do, I mean, up until now, we've been trying to kind of piece together the graphs from this. But if we use that trick where we set the argument equal to the key arguments, right, we end up with, let's see here, let's switch colors. So we have that already. We got the phase shift, we have the period, we have the amplitude. Let's find our key points. So we're going to take this 2x plus pi, set it equal to 0, set it equal to pi over 2, set it equal to pi. We're going to set it equal to 3 pi over 2, and we are going to set it equal to 2 pi. And if I solve each one of these, I actually end up with these values. X is equal to negative pi over 4. This one gives me x is equal to, oh, excuse me, not pi over 4, negative pi over 2. Negative pi over 4, there we go. This one ends up being 0. Then we end up with positive pi over 4, and finally pi over 2. Right, so we have 5 new things to graph here. 5 new points. So we need to get these on the graph, and then I'm actually going to erase this work here. But you can see each one of these is going to give us a new point. So let's see, how do I want to do this? In fact, let me just do this. I'm going to write them down and then erase that. So it's negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. So those are my new anchor points. Okay, so let's go ahead and do that, because I'm not, let's see, it looks like it's pretty symmetric actually around the x-axis, around the y-axis, because we have negative pi over 2, negative pi over 4, pi over 4, and pi over 2. Right, so now it has a period of pi. We can see that from negative pi over 2 to positive pi over 2 has a distance of pi. Now, the amplitude is 3, and it's a negative. Okay, so normally we would start over here. We know we're going to be between 3 and negative 3. Okay, so cosine normally starts up top here and travels down. But because we're starting with a negative 3, it's going to be over here. Oops. I just want to get that a little bit better. Right? And it's going to travel this way all the way up to positive 3, curl back around, and go back down to negative 3, right? So it does that kind of a thing. You notice how easy that was once we had those 5 points? It goes really, really quick. Now, since we're not graphing cosine though, we're graphing secant. And we have to use cosine to make secant. And remember, what secant does is it just launches off of the peaks and troughs of cosine. So our actual graph, well, let's see, we have our asymptotes wherever the cosine is 0 here. And then we can just build the rest of this off our peaks and troughs. Right? It actually does a little bit of that too. Right? But it goes on forever. And so the actual graph here, I'm going to kind of leave a sketch of the cosine in there, but technically it's not there. Right? I keep emphasizing that. Unfortunately, I think a lot of books, because it's easier to explain it to use the sine and cosine scaffolding. Oftentimes, the graphs of secant and cosecant have sine and cosine in them. But that is not the graph of secant and cosecant. It has the final graph is just what's in purple, right? It is not what is in black. Okay, so it's all about finding these key points. So as long as you can get a hold of these key points here, right, you set the argument equal to the old key points is basically what you do, and you see how the coordinate has to transform to be able to accommodate it. Okay. Now those are the main things that I wanted to get through today. So we've seen tangent and cotangent. We played around with that amplitude. And one of the things I really want you to think about, and it's a really good way to get a hold of these things, is understanding where those key points move to and how to find where they move to. And it's by setting the argument of whichever trig function you have equal to the old key values. So in any case, that about wraps it up for today. So until next time, keep your pencils and your wits sharp.